So we've spoken about, or we went through 3 examples of wired or guided media. Twisted pair, coaxial cable, optical fibre, 3 examples of wired media. We've spoken about characteristics of wireless transmission. In particular, we went through the free space path loss model where it gives us an equation that relates, we transmit with some power and we lose power and receive a signal with some received power strength. How much power do we lose across a particular distance? That's what that free space path loss equation tells us. It also relates the fact that our antennas introduce some gain into the system, both a transmit and receive antenna. We're going to finish this topic today with just some quick examples of wireless media. Not all of them, just some common examples that you may or you know about, and then we'll move on to the next topic. So we'll go through reasonably quickly these examples. First, terrestrial microwave. This is the microwave referring to the wavelength of the signals we're using, which indicates the frequency. If we look, I think one of our earlier slides gave the diagram of the spectrum, and it identifies the microwave applications or the microwave range of the spectrum. Terrestrial referring to on the ground. Our transmitters and receivers are on the ground, as opposed to the next example, which is satellite microwave, where we're transmitting up to a satellite up in space. Our signal is not sent along the ground, it's slightly above the ground, so we have a transmitter and receiver at approximately ground level. Such systems are normally point-to-point using dish-shaped antennas, parabolic antennas, where we have one transmitter transmitting to a receiver in a point-to-point configuration. We have some tower and our antenna and our receive antenna. And using point-to-point communications, the antennas are highly directional, meaning the signal transmitted by this antenna goes in one direction only. That is, it's strongest in that direction. In other directions, it's very, very, very weak. So to communicate, both the transmit and receive antenna need to be pointed at each other. Because if we have one antenna, if the receiver's in that direction, if we misalign the transmitting antenna, the signal will go in that direction, it will not be received by the receive antenna. So we have point-to-point links, and that's what we get line of sight. We refer to line of sight communications, that the transmitter and receiver are within the line of sight of each other. They can effectively see each other. And to avoid obstacles, because of the frequencies we use, they do not pass through obstacles such as buildings very well. When the signal hits a wall, that signal attenuates significantly and it comes out the other side very, very weak and it cannot be received. So if there are any obstacles between the transmitter and receiver, then normally they cannot communicate. So hence we need line of sight communications. That's why for some applications the antennas are in fact placed on top of high towers. So buildings, trees and so on are below the signal. The best example is the connection from our other building to our Rangsit campus. We have antenna on top of the other building at this campus and one at Rangsit campus, and those antennas are aligned to point at each other, and they are a point-to-point terrestrial microwave application. No building, no significant building between the two. In fact, originally when they designed that wireless link, there was a problem because they were placing the antenna on one of the buildings of Rangsit, but one of the new dorms was built one of those new dormitory buildings was built, and therefore they had to remove the antenna because it obstructed the signal. So the signals pass through some obstacles, but when the signal hits an obstacle, it attenuates. It gets very, very weak. So if there's a tree in the way, then the signal will be attenuated by that tree, but it still may be successfully received. We just need to increase the transmit power. If there are many trees or a large building in the way, then the signal will not pass through, or what comes out the other side will be so weak that the receiver will not be able to understand. So these terrestrial microwave links are used in long distance communications, so as an alternative to using optical fibre. If it's too expensive or inconvenient to lay cables under the ground, then we could put some antennas on top of towers and have wireless links over tens of kilometres, as opposed to over that distance of 10 or 20 kilometres between our two campuses laying a cable, which is very expensive because you need to get access to dig under the ground under many different property owners. So this is an alternative. If you want to lay cables, that can be very expensive to get the access and to dig the holes to put those cables in. If there are already ducts to place those cables in, it's okay. But if you need to lay new cables, it can be very expensive. It can be very easy to put up an antenna or a tower with an antenna on, and you have a direct link. But of course, obstacles cause problems. Used for TV distribution, for example. TV stations have networks across countries, and in some parts they may use these wireless transmissions to distribute their content throughout, across a large distance. The frequencies used, if we look, I think one of our previous slides, I think some of the higher frequencies used can be affected by the weather, the atmosphere and rain. Especially satellite, the next application, we'll see the frequencies are impacted by rain. That is, the signal hits the water and is attenuated. And therefore, the more rain, the more water, the weaker the signal will be at the receiver. And you notice that, or you may notice that in some cases if you've got satellite TV, and the reception can be poorer if there's a large storm. Used between buildings in some cases. And another example of using similar frequencies is, but not necessarily in a point-to-point configuration, is your mobile telephone. Your mobile phone systems, where it's really a point-to-multipoint, we have a single tower. It's not using highly directional antennas. Normally the mobile phone towers have multiple antennas. Usually sectorized antennas, where they have some antenna which transmits a signal in this area, and another antenna transmitting in this sector, and another one in this sector. So they have multiple antennas pointing in particular directions, and you with your mobile phone have a wireless link to that base station or cell phone tower using similar frequencies and similar technologies. Some examples of the frequency band being used by these technologies listed here, the corresponding bandwidth and the data rate or approximate data rates that can be achieved. This is indicating the approximate center frequency of the signal being sent. Remember, our signals, if we plot as a function of the frequency and the signal strength, our signal contains a range of frequencies from here up until here. We can usually talk about a center frequency and have some bandwidth. So in fact, our signal have a frequency and a bandwidth. At the frequency of around 2 gigahertz, if we use a bandwidth of around 7 megahertz, then we're talking about data rates of around 12 megabits per second. With higher frequencies, we've got a larger bandwidth available and we can achieve higher data rates. So that's one example of a wireless system. In this table, the band is the frequency band. Yes, the frequency. So a signal contains multiple components with multiple frequencies, but we often approximate that signal by talking about, well, what is the approximate frequency being used, or what's the center frequency of that? This may be a frequency of 2 gigahertz. But in fact, the signal, if it has a bandwidth of, instead of 7, say 10 megahertz, then this lowest frequency may be 1.995 gigahertz, and it may range up to frequency of 2.005 gigahertz. The maximum frequency component, the minimum, the difference is 10 megahertz, if I've got my math correct. So we talk about often, in practical situations, the frequency of the signal, which is just the frequency of one component, or the center frequency, say 2 gigahertz, and the bandwidth of that signal. So the band column here is referring to the frequency band, say the center frequency. For another example, your wireless LAN in your laptop uses a frequency band of around 2.4 gigahertz and has a bandwidth of around 20 megahertz to achieve data rates of 1154 megabits per second. Another example of a wireless medium, satellite microwave, using similar frequencies but not transmitting to stations on the ground but relaying via a satellite up in space. Where we have an antenna on the ground, some satellite up in space or in some orbit, and another antenna on the ground. In fact, the satellite has antennas on it, and we transmit a signal up to the satellite, and that relays it down to some receiving ground station. So these are earth stations or ground stations. So in fact, we have two links: the uplink and downlink. Of course, in most cases we want to communicate, or in some cases we want to communicate in both directions, up to the satellite and down, and also coming back. We'll see some different examples. So up to the satellite we refer to as the uplink, and down from the satellite, the downlink. And in fact, the signal sent on the uplink and downlink, usually so we can communicate in both directions at the same time, we use different frequencies. So one frequency for uplink and one for downlink. And what the satellite does is relays that signal. As you transmit up to the satellite, it's an amplifier or repeater. It just sends the signal down to the receiving ground station. As we said before, this refers to the frequency band, the frequency, This is the range of frequencies. So the band, center frequency, bandwidth, the range of frequencies.
So the bandwidth is if the band is greater, the bandwidth you get.
Not necessarily, but quite commonly, the larger the bandwidth, the larger the frequency we have, the more bandwidth is available for that application. But that depends upon the spectrum management, the national organisation or the international organisation that allocates frequencies to particular applications. These are examples of some of the frequency bands allocated for terrestrial microwave. You cannot use any frequency, you need to use one that you have a license for, and they are some of the ones that are licensed. Our satellite, there are different orbits of the satellite for different, provide different types of services. Two common orbits. One is the geostationary orbit, or a geosatellite. This is a satellite that is at such a height above the Earth, about 36,000 kilometres above the Earth, such that as the Earth rotates, the satellite is orbiting, and it's as if the satellite is always fixed above us. So here in Thailand, of course the Earth is rotating, the satellite is also orbiting. If we look up, we will see the same geosatellite all the time, because it's rotating at the same rate as we are. At such a height, the satellite, which has antennas which are transmitting signals down to Earth, provide a coverage of about 1/3 of the Earth's surface. If we illustrate that in 2 dimensions at least, if we have our Earth and we have our satellite, it transmits a signal down, and with the antennas we can cover about 1/3 of the surface of the Earth. Of course, this should be in 3 dimensions. So everything in this area, and also in 3 dimensions, is within coverage of that satellite, can receive a signal from that satellite, and also can transmit a signal to that satellite. So if we've got coverage of about 1/3 of the Earth's surface, to cover everyone on the in the world, then we'd need 3 satellites orbiting in a geostationary orbit. In fact, it's not always 1/3 of the Earth's surface. So having multiple satellites, we can get almost comprehensive coverage of everyone in the globe, in the Earth. An example is GPS for navigation. That uses satellite communications, where there are satellites close to the geostationary orbit, and in fact I think there's about 20 or 24 satellites, such that no matter where you are on Earth, you're within coverage of multiple satellites, and you receive signals from multiple satellites with GPS, and your GPS receiver uses those multiple signals and the timing of those signals to locate where you are, some coordinates. An alternative or another orbit is a lower Earth orbit, where the satellites are hundreds, possibly 1,000 kilometres above the Earth. What that means, because they're much closer, our satellite in the low Earth orbit, a LEO satellite, it is rotating, to be in that orbit is rotating much faster than the Earth is rotating. So if we look up, of course we're always rotating, but if we look up, we'll always see the geostationary satellite as if it's fixed above us. But a LEO satellite, it will be moving. So we may be within coverage of a single LEO satellite for maybe 1 or 2 hours. Oh, actually less than 1 or 2 hours. And maybe tens of minutes. It orbits the Earth every 1 or 2 hours. So it goes around every 1 or 2 hours. So we'll see this LEO satellite 2 hours later. It's gone around the Earth and we'll see it again. So we may only be within coverage for tens of minutes. So if I want to use this for continuous communications, let's say a satellite phone, then we would need multiple LEO satellites to have continuous communications, because if I've got my satellite phone and I'm communicating with one LEO satellite, it's only above me, or I'm only within range for 10 or 20 minutes. Then it moves, or it's moving. So to get continuous coverage, I would need another LEO satellite to come around and provide coverage.
So which one, the satellite phone, GEO or LEO?
Both. That is, there are some systems that use GEO, except we'll talk about a limitation. There's one which is referred to Iridium, the name of a satellite network which uses LEO satellites, and it had a constellation of around, well, originally 66 satellites in a LEO orbit going around the Earth, providing you satellite phone coverage.
So Iridium is GEO.
LEO.
LEO.
Because it's in a lower orbit and because it's moving relative to the user, we need many satellites to provide continuous coverage. With a GEO, we'd need a minimum of 3 satellites to provide coverage of any place on the Earth. The LEO satellites are generally much smaller. The GEO satellites can be much larger and more expensive because the expense is involved in building the satellite and getting it up into orbit. You need a rocket to launch that satellite. And some of them are the size of a bus or so. So they're quite large, quite heavy, and you need to launch them. So satellites in general are expensive to deploy. They last for several to possibly 10 years once they're deployed, and then they need to be replaced. But can provide coverage where other wireless and wired systems cannot get access to. You don't need to have the antennas on, you don't need to have antennas which are located such that we can avoid obstacles like buildings. With a satellite, we can not have to worry about those obstacles. The problem that arises is, especially with GEO, is that because it's 36,000 kilometres away, you can do the calculation of the propagation delay, the distance divided by the speed of light. And to transmit up and come back down is about 1/4 of a second. So the delay to communicate with a satellite is about 1/4 of a second, 250 milliseconds, plus other delays. And it starts to be a problem with voice communications. There's a delay between when you speak and the other person hears. And with internet communications, there's a large delay between when you press or you visit a URL, you select a link, to when the request is received by the server and then the web page comes back. So it's inconvenient for some applications. LEO satellites are better with terms of delay because they're much closer, but much more complex to deploy and get coverage across a wide area. Example of a point-to-point communications in the satellite. And also we can have a broadcast, a point-to-multipoint communications, where we have a single transmitter, such as a transmitter which is distributing TV for satellite TV. It sends the content up to the satellite transmits down. Anyone within the range or the coverage of that satellite can receive that signal. We say the coverage of the satellite is the footprint of that satellite. So anyone within the satellite's footprint can receive, if they have a receiving antenna. So this is like satellite TV. If you have the antenna, you can receive the signal and watch the TV. And everyone receives the same signal. This is usually one-way communications. With satellite TV, you receive TV. You don't send anything up to the satellite. It's just in one direction. up from the transmitter to the satellite and then down to the user. So satellites used in TV distribution because we can cover a wide range of people in this one-way communications. Some long-distance telephone systems, especially in the past, not so much now, but still satellites are used between countries, for example. Some companies may have their private network. You want a link between the offices that you have around the globe in different countries. Then using a satellite link can be convenient. You have these antennas on the top of your building that transmit up and receive from the satellite. And things like positioning, GPS, or location service. Just some examples of applications of satellites. And perhaps the main one is defence or military communications, where you do not have the ability to deploy the antennas on the ground. Satellite communications provides very quick setup of the network. You just have your receiver and you can instantly communicate. You don't have to deploy cables, you don't have to put towers up, you can immediately communicate. Just one example you have a look at. One example you can look in your own time is IP-Star is a Thai-based satellite provider, and it uses a geostationary satellite, and it provides coverage of most of Asia and Australia, and it's quite a popular service for satellite internet. So you and I can subscribe to the service where you get a dish, a transmitting and receiving dish for home, and you can transmit up to the satellite as well as receive from the satellite and use it as your internet access. And if you don't have ADSL, that is, if you cannot get ADSL because it's not available in your home, then one of the options, in some cases one of the only options, is to use satellite internet access. And IP-Star is one example of a provider. On their website, you'll find some specifications of the satellite and the antennas or the transmitting equipment, the terminals that you have in your home. It talks about the frequencies, the transmit power, and the data rates that you use or that are available. Generally, slightly lower data rates than wired internet access for the same cost. So maybe you're talking about hundreds of kilobits per second. And the problem is delay. As we said before, the large propagation delay means some internet applications are not very convenient to use because of that large delay. And last quick example, broadcast radio. That is using omnidirectional antennas, using frequencies from around 30 megahertz up to several gigahertz for things like FM radio. So FM radio is an example here. Some television transmissions, UHF and the VHF frequency bands, and some wireless networking applications. Some wireless LAN, wireless communications use omnidirectional antennas and are considered or classified as broadcast radio. Broadcast, because of using omnidirectional, the signal goes everywhere. Whereas here we're talking about signals going in a particular direction, also to the satellite. So that's very quick coverage of some examples of wireless media. There are others, but that's all that we need to go into detail for this course. The frequency bands. So if you go back to, I think, the second or third slide in this handout, you'll see this table of the spectrum. And UHF and VHF refers to, let's go back. Right back to the start, I think. Where were we? In fact, here, this table has it as well. There's another plot or another diagram at the start of the lecture notes. This one has it. VHF, very high frequencies, just the name of the band. Frequencies from 30 megahertz up to 300 megahertz. UHF is from 300 up to 3 gigahertz, 300 megahertz up to 3,000 megahertz. Ultra high frequency. So it's just referring to the range of frequencies used. They have different characteristics, the signals. And different applications or countries allocate spectrum in these bands to different applications. Normally for TV transmission, VHF for FM radio, UHF for mobile phone, cellular telephone applications. And you can see the other frequency bands there as well. Yep. The internet, in most cases, it's wired communications. Wired. That is, wires, cables, physical wires, not wireless. Most of the connections between countries, within cities, where possible, use optical fibre or other wired communication systems. But in cases where it's not possible or it's expensive to use that, then wireless can be used. Of course, from the end user's perspective, us, wireless is also used to provide the convenience and mobility. Your mobile phone, your laptop. Because it's wireless, we can move around and it's convenient. We don't have to plug in cables. But from the switch which this, or the access point out there connects to, or this computer connects to all the other components that form the core of the internet, most of it is wired. There would be some wireless links, but most would be wired where possible. Wireless provides us the opportunity for mobility. We can move and still communicate. With wires, that's very hard. Convenience, we don't have to plug in the wire. So it's very easy. We can immediately transmit without having to set up the communications link. And related to that, deployability. That is, it's often easier to deploy wireless than setting up a network with wires. Like satellite, if I'm in a remote area of the world, I don't have any, there's no wired infrastructure there, then I can use a satellite phone to communicate in that case. Iridium is the name of one of the LEO, low Earth orbit satellite systems. It was deployed with about, I think originally 66 satellites. That is, over a number of years, they launched 66 satellites above the Earth in some orbit, such that if you look up, there's always one satellite above you. It's moving, but when that one moves out of your, or that moves away out of the, over the horizon, you cannot see it, a next one comes along. If you look a picture of the Earth, there's always satellites all around the Earth. Of course, this is just in 2 dimensions. In 3 dimensions, they're covering the Earth, providing a network for communications between any point. I will transmit up to this satellite, and that either transmits down to a receiver, or in a more complex scenario, transmits to this satellite, and to this one, and then down to a receiver here. That was one of the, perhaps the, well, the only major one that was built. All of these signals can, again? No, not necessarily. Different frequencies have different characteristics. Some of them are mentioned here. Visible light cannot, infrared cannot. The different, it's to do with the physics of waveforms moving. Remember, if you go back to I don't know, high school physics where you send light through some prism and the frequency, the different colour components go in different directions. That is, they pass through obstacles in different manners. That's what it's related to. So different frequency signals have different characteristics in terms of passing through obstacles. Some are obstructed by water. Some frequencies are obstructed by water or attenuated by water more than other frequencies.
Is that like from alpha rays, beta and gamma rays? Are there different penetration properties?
Yeah, that sounds like it's close. But there's more characteristics than just that. Yeah. So, when choosing a wireless system, you need to consider the frequency it uses. But the other thing, and what application you want to use it for, what distance do you want to communicate? If you did the homework, you would use the free space path loss model and did a calculation of how far you can communicate. Remember, the distance is related to the frequency, or the path loss is related to the frequency. That homework, especially the calculation with the free space path loss, make sure you've attempted that. If you haven't already, go and do it this week. It's very good practice for the exam and the quizzes. Let's move on to the next topic. Signal encoding techniques. We'll try and get halfway through this today, so we'll go through some parts quick, because some of this we've seen before. We know that data can be analog or digital. My voice is analog data, my computer generates digital data, bits. And we know that signals which transmit or communicate that data can be either analog or digital. So in fact we have 4 combinations. We've already mentioned or compared the 4. We're going to now talk about how do we encode the data into signals. We have our data, we need to transmit a signal. What's the mapping from that data into a signal? How do we what are the techniques for encoding those signals? And there are 4 different combinations. We'll go through each of them. So some terminology and introductory concepts. The signal that we transmit needs to be designed and chosen to make optimal use of our transmission medium. If we have a wireless transmission medium, we can only use a particular bandwidth, because that's all that's allocated at a particular frequency. We need to choose a signal that uses that bandwidth optimally to transmit our data. We always want to conserve bandwidth. Bandwidth has some cost associated with it. We want to use as little as possible to transmit as fast as possible. But we know that, of course, bandwidth is related to data rate. We want to do things like minimize errors. We want to construct a signal that when the receiver receives that, even with noise, that there's a very low chance that errors will be detected or errors will be incurred. We have digital signals and analog signals that can be transmitted. So digital signaling, we can transmit either digital or analog data, and that's encoded into a digital signal. We'll talk about the different encoding techniques in this topic. We can sometimes represent them as some equation. The data, some data g as a function of time, and we create a signal, some function x, as a function of time. With analog signaling, we transmit our data, either analog or digital, as an analog signal. And how we do that is that we have this analog, what's called a carrier signal. And we use the process of modulation. So we take our data that we want to transmit and we encode that onto a carrier signal of a particular frequency. So my wireless microphone transmits to the wireless receiver here. My voice is the data we want to communicate, and the wireless signal being transmitted there is a signal. My voice is encoded onto that signal. How does that work? We'll go through how that works in this topic. How that encoding works. Just some terminology. In fact, this terminology we will not use until the end, but we'll just mention it. The input signal, my voice, for example, is often called the baseband signal. And we modulate the carrier signal. The result of that is called the modulated signal. That's what's transmitted. Say from my wireless microphone to the wireless receiver, there's a modulated signal sent. The original signal was my voice, or the baseband signal. How that modulation works is one part of this topic. I think we've seen something similar to this in a previous lecture. With digital signals, we talk about taking our input data and encode that to get a digital signal that looks, say, like this, is transmitted. The receiver has to decode. They receive a digital signal, they need to get the original data back. So we have an encoder at the transmitter, a decoder at the receiver, or a codec if we combine them together. With analog signals, we have the input data. We use a carrier signal with some frequency, and we do modulation at the transmitter. We get an output analog signal, the modulated signal. We transmit that across our link. The receiver needs to demodulate. So together we refer to a modem, a modulator and demodulator. We're going to go through the 4 different parts. Okay, if we have digital signals, we can have either digital or analog data. If we have analog signals, we can have digital or analog data. So 4 different combinations of how to do the encoding or modulation. All 4 of them are used in practice, these 4 combinations, digital data, digital signal, and so on. Some of the differences between them, or some of the advantages, using digital signals, or a fully digital system, digital data and digital signals, generally the digital signaling can be less expensive of having to convert between analog and digital. So that's one of the advantages of using a fully digital system. In some cases we have analog data. My voice is analog data, it's not digital data. So some cases we'll transmit that as a digital signal rather than as an analog signal, because again we can take advantage of digital transmission techniques, repeaters, the ability to detect and correct errors. In some cases we cannot send digital signals, we can only send analog signals. Your telephone only transmits analog signals, or the telephone network. So if you're talking, you're generating analog data on your home telephone. If you attach your computer, the computer generates digital data, but the network only carries analog signals, and that's where your modem comes in. Converts the digital data to analog signal. So we need techniques to do that. Some systems only propagate analog signals. We cannot use digital signals. And of course, in some cases, again, we have analog data and we transmit it as an analog signal. In the last part of the last section of this topic, we'll see the advantages and the issues with that. Let's go through the first case. How do we send digital data as digital signals? We've seen this in many examples already. You have bits, zeros and ones. Very simple scheme. If you want to transmit bit 0, send a high voltage signal for some period of time. If you want to transmit bit 1, send a different voltage, a low voltage signal. So our digital signal is a sequence of discrete voltage pulses. So for some period of time we maintain a voltage on the line, and that's one pulse. And then for the next period of time maintain a voltage, and that's another pulse. We can refer to each pulse as a signal element. And the data, the binary data, is encoded, each bit or data element is encoded into signal elements. And the very basic case we've seen before, encode binary 1 into a low voltage, binary 0 into a high voltage. And also we've seen before that can lead to, we can have a signalling rate and a data rate. Quick repetition of that case. Have our data, 6 bits of data to send. If we use this scheme to encode, then our signal to transmit bit 0, send high level, a high voltage for some duration of time. Bit 1, a low voltage. Bit 0, 1, another 1, and 0. This is a signal element, 6 signal elements here, or 6 pulses. The input data, the output digital signal. If the pulse duration is 1 millisecond, our signalling rate also referred to as modulation rate, or baud, or measured in baud. How many signal elements per second? Well, if there's 1 every 1 millisecond, we'll have 1,000 per second. SE, 1,000 signal elements per second. Each pulse or each signal element represents 1 bit. Therefore, our data rate is 1,000 bits per second. We've seen this example before, or a similar one. And we can do something different. We can have a different encoding scheme. Instead of mapping 1 bit to 1 signal element, we can have 4 different signal elements and map 2 bits to a signal element. Here our scheme was low voltage bit 1, high voltage bit 0. A different scheme the 2 bits 0, 0 correspond to the signal element with a high voltage, plus 5 volts as an example. 0, 1 as a slightly lower voltage, plus 1.6 volts. 1, 0 as a different voltage. And 1, 1 as another voltage. That is 4 different levels. And now to transmit our sequence of digital data, we look at 2 bits at a time, 0, 1. If we draw our signal, we're going to have 4 levels, plus 5, plus 1.6, minus 1.6, minus 5. The first pulse, we want to transmit the data 0, 1. Therefore, we will send a pulse for 1 millisecond at 1.6 volts. And then we have the data again 0, 1, the next 2 bits, another pulse at 1.6 volts, and then the last 2 bits 1, 0, a pulse at minus 1.6 volts. This is our digital signal using this encoding scheme. What's our signalling rate? Our signalling rate?
Signaling rate is 1,000. Is that right?
The second one.
Oh, the second one. The second one is 1, 2.
Signalling rate. If each pulse is the same as in the first case. Each pulse is 1 millisecond. One pulse in 1 millisecond, signalling rate. 1,000 in 1 millisecond, 1 pulse or 1 signal element. In 1 second, 1,000. So our signalling rate is the same as here. That is, this pulse lasts for 1 millisecond. 1 millisecond, 1 millisecond, 1 millisecond. Just as an example, that 1 millisecond. Same here. 1, 1, 1, 1, 1, 1 millisecond. The same signalling rate, 1,000 signal elements per second, but now our data rate. Each signal element represents 2 bits. The first signal element represents these 2 bits. So our data rate would change to 2,000 bits per second. So we recall the difference between data rate and signalling rate. And this is about the number of levels. When we refer back to the Nyquist equation, M was the number of levels. Increasing M increases our data rate when we keep other things the same. So, when we transmit a digital signal, how can the receiver, what determines how well the receiver can understand the received signal? Some factors we already know about. If we transmit a digital signal, noise can introduce bit errors. This is a diagram we've seen before. We have a signal, we have noise. This is the received signal. The receiver samples, measures according to our scheme. If it's low voltage, bit 1. If it's a high voltage, bit 0. If we have a large amount of noise, like at this point, and at this point, we can get bit errors. If the noise increases, there's a more chance of errors. If our data rate increases, there's more chance of errors. Consider in this case, the 2 errors occurred because of these large pulses of noise. This large part of noise meant the bit 0 changed to bit 1. That was a bit error. And this large piece of noise caused a bit error. If we had the same noise, but doubled the data rate, then there's potentially more bits impacted by that noise. In this example, only 1 bit was impacted by this noise. And therefore we got 1 bit error here. And similar, 1 bit was impacted by this noise, leading to 1 bit error. If we had double the data rate, this noise would impact upon 2 bits. And therefore there's a chance of getting 2-bit errors. And this pulse of noise would impact potentially on 2 bits and a higher chance of more bit errors. So, what impacts on the successful reception? Different factors: signal to noise ratio, amount of noise compared to the signal strength, the data rate and the bandwidth. If we increase our data rate, generally increases the rate at which errors occur, the bit error rate, BER. So increasing our data rate can lead to more errors, which is a negative. Also, we know increasing the signal-to-noise ratio decreases the bit error ratio, bit error rate. Why? Well, remember, signal-to-noise ratio, increase the noise will increase the bit errors. Decrease the noise will decrease the bit errors. Decrease the noise increases the ratio. If noise goes lower, SNR goes higher and the bit error rate goes down. More noise, more errors. This is essentially what this is saying. Increase the bandwidth increases our data rate. So these factors impact on how successful we can receive. Another factor is how do we encode the data? Do we use this scheme? Do we use this scheme? Or perhaps a more complex scheme, the encoding scheme used? Let's look at some example encoding schemes. Some of the examples, or common ones, are described in this table, but they're illustrated by an example in this diagram. At the top is the digital data we want to send. These are names of different encoding schemes, and this is the digital signal generated using each encoding scheme. Which one is this? Our very simple case. Of those 6 encoding schemes, which one is the one we've used in many examples? The first one, obvious. Bit 0, high signal, say a positive voltage. Bit 1, low signal, a negative voltage. So that's all this one is. It's called non-return to zero level. The voltage does not return to zero. It's always at either positive or negative. So that's all that first scheme is, the very basic one that we've used in examples before. Second one, non-return to zero, invert on ones. I means invert here. See how it works? Whenever we have a bit 1, we change the level. Whenever we have a bit 0, we keep the level the same. All right, we start with a low level just to get started. We have a bit 1 to transmit. So the first bit was a 0, the next bit is a bit 1, therefore we invert the level. We go from low to high. We get to here, we have a bit 0 to transmit, therefore we maintain that high level. We do not invert. Bit 0, maintain the level. Bit 1, invert. Move to a transmit at a low level. Bit 1, invert again, and so on. Whenever there's a bit 1 to transmit, we change the voltage level from positive to negative or negative to positive. So that's just a different encoding scheme. We'll talk about why we have different ones. I will summarise that in one of the later slides. But let's just go through 2 more examples, or 2 different ones first. Another one, bipolar AMI. AMI is alternate mark inversion, where mark refers to bit 1s, a bit 1. What we do is we have 3 levels. 0 voltage, a positive and a negative. So we have 3 levels here. Bit 0, we have 0 voltage. And there's no line signal. So if we draw a line through here, this is the 0 voltage level. Whenever we have bit 0, 0 voltage. Whenever we have a bit 1, we'll use a voltage level opposite to what the previous bit 1 was. Let's say the first bit 1, we use a high voltage. The next bit 1, alternate to a low voltage. The next bit 1, high voltage, low voltage. High, so if we kept looking, if you look at the bit 1s, you'll always see the alternation. High, low, high, low, high, low, and so on. Zeros, 0 voltage. 1s alternate between high and low. When the receiver receives this signal, it just needs to determine, okay, if it's 0 voltage, it must mean a bit 0 was transmitted. If it's high or low, it must be a bit 1 transmitted. Another example in a common scheme, the Manchester. Yeah? Have a look at the pseudo-ternary and work out the difference between that and bipolar AMI. A good quiz question. It's described in the lecture notes. We're not going to go through it all now. It's very simple though. You'll have a look and you'll see the difference. Manchester. In these encoding schemes, we were changing the signal level when the bit changed. With Manchester, we changed the voltage, the level, in the middle of the bit. With Manchester, if we want to transmit bit 0, we'll have high to low. That is, in the middle of that bit, we'll change from high voltage to low voltage. And the opposite for bit 1 will change from low voltage to high voltage. So we could draw that. Bit 0 is always going to be this shape, high to low, and bit 1 the opposite, low to high. And that's all we get with the Manchester encoding. There are different, and there's others, differential Manchester, and there's even others as well. Why do we have different ones? They have different characteristics. One of them, often we'd like to be able to, the receiver needs to know when does the first bit start and when does the next bit start. The timing or synchronization is important. That is, the clock of the receiver, even if it is different from the transmitter, there's some difference in the clocks, it needs to know when is the first bit. That is, if this is 1 millisecond, the clock of the receiver may be slightly off. What is really 1 millisecond is thought of as only 0.9 milliseconds. So sometimes it's useful for the receiver to be able to synchronize to know exactly when does the next bit start. One way to do that is to use the signal encoding to detect when does one bit change into a next bit. If we looked at one of the first two, let's say our data had a long sequence of zeros. In non-return to zero level, if we had 100 zeros to transmit, we'd have the same voltage level for each of those pulses. Nothing would change. And that can make it hard for the receiver to detect, well, when does the next bit come, especially if its clock is not synchronized. What about with Manchester? If we have 100 zeros, the voltage level is always changing. It would look something if we had Manchester encoding with all zeros, it would look like this. If we had non-return to zero, it would look like this. The receiver can use this change to indicate, okay, this must be a new bit. If we changed here, a new bit has arrived. Here, when does a new bit arrive? It cannot detect any information from this case. So one advantage of some of the encoding schemes is that it can help with the receiver to synchronize its clock with the transmitter. Another advantage of some of the encoding schemes is that it can help the receiver to detect errors. Remember, this is what's transmitted. What is received may be slightly different because of noise. Let's consider an example. With, again, non-return to zero level, this is I'll draw a receive signal. It's not related to what we have here. There's 1, 2, 3, 4, 5, 6, 7 pulses. And now using bipolar AMI. I'll draw an example receive signal. In fact, we have 3 levels. Two different receive signals using 2 different encoding schemes. The data may not be the same, that's not the point. Which one has an error? The answer is 1, or is non-return to 0, bipolar AMI, both, or neither. Where is the error? So this is what the receiver receives. Bipolar AMI, why? The last one? It does not alternate. Good. Bipolar AMI, 0 voltage for bit 0, alternates between high and low for bit 1. 0 voltage, okay, 0, high, 0, low, 0, low. If the receiver receives this, it detects an error. It doesn't expect to receive because we've got high, low, low. It should be high, low, high, low, high, low, and so on. So immediately, using this encoding scheme, the receiver can detect an error. We cannot do that from this encoding scheme. We don't know whether this is exactly what was transmitted or not. Here, we know this is not what was transmitted, because the transmitter would never retransmit high, low, low. So some encoding schemes have inbuilt error detection, which is useful. So we'll summarise on some of the encoding schemes in a moment. You don't have to remember all of them. You should remember the first 2 at least. If I ask you, here's some data, draw me the digital signal using non-return to 0 invert on 1s. You should be able to draw the signal. I won't ask you to remember the encoding for Manchester, but I may give you in a quiz or exam a description like this. This is a description of differential Manchester. Here's the data, draw me the signal. Or here's the signal, what's the data? So just be able to interpret the descriptions. The first 2 you can remember, they're easy. The others you don't need to memorise. And there are others as well. 2 that were not shown, B8ZS and HDB3, variations of bipolar AMI, but to avoid having a long sequence of, or a long pulse of the same level, they introduce some changes in the voltage when we have a long sequence of bits. You can see the descriptions in the slides. We're going through some of these quite quickly because, well, we've seen the concepts before, especially non-return to 0 level. Other than that, it should be reasonably simple. It's a way to encode bits into a signal. You can compare the different schemes, and some of the factors that they compare on is what's the spectrum of the signal generated. There are some different properties we'd like. We'd like to minimise the bandwidth, so minimise high frequency components, avoid DC components, allow synchronization of the receiver's clock to the transmitter, detect errors, is a useful feature. Avoid interference, so some schemes provide better avoidance of interference than others. And keep the complexity of the transmitter and receiver low. The more complex the scheme, the harder it is to implement and the higher the cost to implement. We're going to skip over these slides, or some of these slides here. They just show some comparison in terms of the bandwidth occupied by the different schemes. This is the frequency component, so bandwidth of the signal. We'd like to minimize the bandwidth and avoid components or signals with zero frequency, a DC component. So some of the better ones are these two, B8ZS, HDB3, and the bipolar AMI are considered some of the better ones in terms of the spectrum of the signal that they generate. Have a look at those slides in your own time or a description in the textbook for more details on that. And in fact, this describes bipolar AMI, Manchester, and some other schemes, how they've been developed. And the last two more complex ones, B8ZS, HDB3. And some examples of those last two. You see these two based on bipolar AMI, but if we have a long sequence of zeros, for example, with bipolar AMI we get a long sequence of zero voltage. That can be bad from the receiver's perspective, so we introduce some changes with these two approaches so that the receiver can synchronize with the transmitter. Just quickly, because we want to get on to the next one as well. Some example technologies where these schemes are used. USB devices, RS232 serial ports use non-return to zero. Wired internet, wired LANs, Ethernet, uses Manchester encoding. And some of the wide area network technologies use the multi-level HDB3 and so on. So they're used in practice for when we have digital data and we need to send digital signals. What about the next case? We have our digital data, but we need to send analog signals. Like our home internet, our computer generates bits. Our telephone line only sends analog signals. We use our modem to convert those bits into analog signals. We'll just go through that one today. So this is where we want to transmit digital data over some media that supports analog signals. A telephone network, a terrestrial microwave system. And we use a modem to convert the data into signals in some frequency range. The frequency range that the medium supports. There are three basic techniques. We're sending analog signals, so we can think of it as our sine wave. With the signal that we generate, we can vary the amplitude, phase or frequency, leading to amplitude shift keying, phase shift keying and frequency shift keying. If we draw or make note of our equation for our basic sinusoid, that's an equation we've seen many times. What we want to do is we have our input bits, zeros and ones. We generate an output analog signal. What we can do is change one of these three parameters, peak amplitude, frequency or phase, and depending on which bit we want to send, we set them to a particular value. This illustrates those three cases. We have some digital data at the top that we want to send, and ignore the digital signal there. Here is the output analog signal if we use amplitude shift keying. We could say the scheme in this case is if we want to transmit bit 0, set the amplitude to one level, 0 in this example, keep the frequency and the phase to be the same. In this case, the frequency doesn't matter, maybe it's 2 and the phase is 0. And if we want to transmit bit 1, set the amplitude to a different level, keeping the frequency and the phase the same. And we see the output here. Bit 0, amplitude of our sinusoid is 0, which is just no signal. Bit 0, amplitude is 0. Bit 1, amplitude is 1, or some positive value. So we get our sinusoid signal for our analog signal. Bit 1, 0, 1, and so on. So that's it. Just change our analog signal, in this case change the amplitude of the analog signal whenever the bits change. And the other two, frequency shift keying, phase shift keying. The B refers to binary in that we have two levels. Change the frequency. Bit 0, some low frequency, maybe a frequency of 1. Bit 1, a higher frequency, say a frequency of 2. So the receiver receives a signal. If the receiver receives this, it needs to, over this period, determine what is the frequency of this received signal. Okay, it's 1. That corresponds to a bit 0 being received. Here, the frequency is 2, or it's a higher frequency. Therefore, a bit 1 is received. And similar for phase. Remember, the phase is the shift of that signal along. So here we have a phase where we go down first, and with a bit 1 we have the normal phase, or phase of 0. By changing any of those three parameters of our simple sinusoid, we get our shift keying techniques. The way to transmit digital data as analog signals. Amplitude shift keying is generally inefficient compared to the other two. It uses more spectrum, so it's used when we have very low data rates, 1 kilobit per second on very old lines, or when we have a lot of bandwidth available, like on optical fibre. Frequency shift keying is commonly used in some voice communications, in coaxial cable, and in some radio or wireless systems. And phase shift keying, commonly used in some wireless transmission systems. We can extend them to include multiple levels. In the previous diagram, we just had two different levels. One amplitude or another, one frequency or another. We could have 4 different levels, 4 different frequencies. Each frequency represents 2 bits. The same concept as when we had our digital signalling where we had 4 levels, each level representing 2 bits. We can do that with these approaches. Commonly, frequency shift keying is extended to m different frequencies, giving us a higher efficiency, higher data rate, but more chance of errors. And some examples, phase shift keying. If m equals 4, we have 4 different phases. We get this special case of quaternary QPSK. And in fact, we can combine some together. Amplitude shift keying with phase shift keying. 2 different amplitudes, 4 different phases, for example. to give 8 different levels. And a common thing is combining phase shift keying with amplitude shift keying, and we get the name quadrature amplitude modulation, QAM. And that's commonly used in ADSL and wireless systems like wireless LAN. So, we're going to finish there. One thing similar to with the digital signaling, digital data, here, given some signal, and if I say this signal is using frequency shift keying, you should be able to answer, okay, this is the data that was transmitted. Or to create a signal, here's the data, combine amplitude shift keying and phase shift keying, draw the resulting signal. So have a look at those 3 examples on the previous slide to make sure you understand the difference between the 3 and how to combine them together. Let's finish there. So tomorrow we'll just summarise on those 2 techniques and go through the next 2. What happens when we have analog data to send, not digital data?